You will now step from a set of transition rules defined for a given BM scale to the calculation of so-called transition probabilities. And these express the probability that a policyholder moves from one level in the scale to another level in a single step or via multi-steps. And to express these probabilities, let us assume the random variables n1 and t and so on are independent and Poisson distributed with mean theta. Now recall that this variable nk is the random variable which expresses the number of claims reported by the policyholder during year k. And the mean parameter theta, that is the result of the a priori pricing model that we put into place. And this captures the riskiness of the policyholder based on his a priori risk factors. So we denote the trajectory of a given policyholder through the BM scale with a collection of random variables, L1 theta, L2 theta, and so on. And each of those random variables takes a value between 0 and s, which is, of course, the set of possible levels in the BM scale. But to emphasize the dependence upon the annual expected claim frequency theta, we're going to include the theta in our notation. Indeed, one may expect that the path which is followed by a policyholder through the scale depends on his a priori risk factors, and that's exactly what the theta captures. So therefore, the inclusion in the notation used here. So this particular notation, Lk theta, it does not mean that those Lk's are functions of the parameter theta, but it only means that their distribution, so the levels that they take and the probability with which they take a certain value, that this distribution depends on the a priori mean theta of the policyholder. The one-step probability for a policyholder with annual claim frequency theta to go from level L1 to level L2 is denoted with P L1 L2 theta, given that the policyholder occupies level L1 in year k plus 1, so that is between time k and time k plus 1, then he will be at level L2 in the next year with this particular probability P L1 L2 theta. Naturally, of course, these levels L1, L2 take values between 0 and 1. So this is our one-step transition probability in the scale. You will now work with these transition probabilities, and you will derive some insightful properties and results. First of all, the P, L1, L2, they are probabilities, so they take values between 0 and 1. Moreover, since a policyholder either has to stay in level L1 or will move to any other level in the scale, the sum of the probabilities over all possible values that the L2 can take, that sum should be equal to 1. Using the law of total probability, you can express the transition probability as follows. So what we're here going to do is we're going to condition on the number of claims reported during year k plus 1. Indeed, it's the combination of the level that is occupied by the policyholder during year k plus 1 and the number of claims reported in that same year that determines which level the policyholder will occupy in the next year. So the first conditional probability that you recognize here in the expression can be expressed via the transition rules for the general setting of n claims being reported. So this T, L1, L2, n will be equal to 1 if the policyholder moves from level L1 to level L2. When n claims are reported, will be 0 otherwise. And for the second probability that you recognize here, we're going to give some more explanation. So that is here the probability that nk plus 1 equals n, given that lk is equal to L1, right? So here lk is the position occupied during year k plus 1. And this depends on the random variables n1, n2, and so on up to nk. The number of claims reported in all previous years. So the probability here simplifies to a Poisson probability. That is the probability that nk plus 1 equals n for a Poisson distribution with parameter theta. And the reason that this conditional probability simplifies to this marginal probability is because of the independence between the nk plus 1 random variable and the random variables n1 up to nk that determine the level random variable lk. So you're here using this assumption of independence. Now the transition probabilities allow the actuary to compute the probability of any trajectory in the scale. For example, consider the probability that a certain policyholder with an expected annual claim frequency equal to theta. So consider that he is in levels L1, L2, and so on up to Ln at time points t equal to 1, equal to 2, and so on up to time point n. So we're gonna denote this probability as follows. So given that the policyholder started in level L0 at time 0, what is then the probability that he will be in level L1 during the second year, in level L2 in the third year, and so on and so forth. So this implies that the policyholder goes in a single step from level L0 to L1, then from L1 to L2, and so on and so forth. So the probability of this particular trajectory results as the product of the applicable one-step probabilities. So in fact, you can express the above probability as a product of conditional probabilities. And for each of those conditional probabilities, you will use the Markov property. And by using this Markov property, the probability of the whole path, of the whole trajectory that you're considering here results or simplifies to a product of one-step probabilities. So indeed, you rely on the Markov property underlying the transitions in the BM scale when you express the probability that a policyholder with annual expected claim frequency theta, that he will be in level Ln during year n plus 1, given the trajectory that this policyholder made from time 0 to time n. When you simplify this conditional probability to the one-step probability printed here on the right-hand side, the probability p l n minus 1 ln, when you do this simplification, you're actually using this Markov property, right? The future level only depends on the present level occupied in the scale. It does not depend on the trajectory that brought a policyholder to this particular level. We put these one-step transition probabilities, we put them together in a one-step transition matrix, P theta, and the first row in this matrix displays the one-step transition probabilities expressing the possible transitions from level 0. The second row represents the probabilities attached to the possible transitions from level L1, and so on and so forth. Now, using the connection between the one-step probabilities and the transition rules, as developed on sheet 22, you can rewrite this matrix P theta as a function of Poisson probabilities on the one hand. That's the expression that you recognize here. It's the theta to the power k divided by k factorial multiplied with the exponential of minus theta. So that's the Poisson probabilities on the one hand. And on the other hand, you also recognize the matrix Tk, which was the matrix containing the transition rules in case the policyholder reports k claims at fault. And the operations that you see over here in this expression, they work element-wise, and they rely on the assumptions of independent and Poisson distributed random variables nt, right? So you're now ready to derive the one-step transition matrix, the P theta, for both the BM scales that we introduced and studied earlier on in the course. And first of all, we consider the -1 top scale. The first row displays the one-step probabilities for a policyholder who currently occupies level 0 in the scale. If he reports 0 claims, he stays in level 0. But this happens with Poisson probability, the exponential of minus theta. That's the probability in a Poisson with parameter theta to report 0 claims. If the policyholder reports 1 claim or more claims, he goes to level 5 in the scale. And that happens with probability 1 minus the probability to report 0 claims in a Poisson distribution with parameter theta. So that's the probability 1 minus the exponential of minus theta. Try to explain the other rows, the other probabilities printed in the rows of this transition matrix in a similar way. Things will become slightly more complex when we are working with the -1 + 2 scale. Let's start again with the probabilities printed on the first row. The first row considers a policyholder in level 0 of the scale. If he reports 0 claims, he stays in level 0. And that scenario happens with a Poisson probability that is equal to the exponential of minus theta. But if the policyholder reports 1 claim, he moves to level 2 in the scale. And that's going to happen with a probability theta multiplied with the exponential of minus theta, which is the probability in a Poisson distribution with parameter theta to report a single claim at fault. If the policyholder reports 2 claims, he goes to level 4. And that happens with probability theta squared divided by 2 multiplied with the exponential of minus theta. Finally, if he reports 3 or more claims, he ends up in the top level of the scale. That's level 5. And this happens with the following probability. Now you have to be a bit careful. It's the probability to report 3 or more claims according to a Poisson distribution with parameter theta. And you can express this probability as 1 minus sigma 1, where the sigma 1 in our notation here is the sum of the following probabilities. The probability to report 0 claims, 1 claim, or 2 claims. Try to explain the other probabilities that you see printed in the other rows of this transition, of this probability matrix in a similar way. Next to the one-step transition probabilities, you can also consider the multi-step transition probabilities. And we then consider the probability to go from level I to level j in the scale in n steps. For example, let Pij theta n, where the n is between brackets and is used as a superscript, let that be the probability to be in level j during year k plus n plus 1, given that you were occupying level I during the year k plus 1. So that's an n-step transition probability. And to find this n-step probability, you will consider all the possible transitions from I to j in n steps. So let the intermediate levels that you occupy be denoted with I1, I2, and so on up to In minus 1. The probability to follow the trajectory from I to I1, from I1 to I2, and eventually from In minus 1 to j, that's the product of these one-step probabilities, the Pi, I1, the Pi1, I2, and so on and so forth. And if you then sum over all the possible values that these intermediate levels can take, you get the requested n-step transition probability. Okay, if you put all of these n-step probabilities in a matrix, you retrieve the n-step transition matrix composed of the n-step transition probabilities. The following property reveals an interesting way to obtain this n-step transition matrix. Because for all integer n and m, the n-step transition matrix, on the left-hand side of the equation, equals the nth power of the one-step transition matrix, which is printed at the right-hand side of the equation. And you can also then, as a consequence, see that the n plus m step transition matrix is the product of the n-step transition matrix with the m-step transition matrix. And we're going to prove this property by induction. So the property definitely holds for n equal to 1, because then it just states that the one-step probability matrix is equal to the matrix P, which is true because that is the one-step transition probability matrix. Let us assume that the property holds for n, and then we want to show that it's also going to hold for n plus 1. So consider the n plus 1 step transition probability to go from level I to j. At time n, the policyholder will occupy some level L between 0 and s. So the n plus 1 step probability can be written as an n-step probability to go from I to L, multiplied with the single step probability to go from L to j. And now we sum over all possible values that this intermediate level L can take. And what you recognize in this expression is a matrix multiplication. It's a multiplication between the matrix Pn, that's the n-step transition matrix, and the matrix P. And using the reasoning by induction, we know that the n-step transition matrix is the nth power of the matrix P. So the matrix multiplication that you recognize here in the equation gives us then the n plus 1 power of matrix P, which concludes the proof. So we have the property that the n-step transition matrix, transition probability matrix, can be calculated as the nth power of the single-step transition probability matrix. Using this property, it is straightforward to understand the expression at the bottom of the sheet, which says that the n plus m transition matrix equals the product of the n-step and the m-step transition matrices. And this property is also known as the Chapman-Kolmogorov equation. From the one-step and the multi-step transition probabilities, we will now move on to the distribution of the state random variable Lk. So this is the random variable that expresses which level the policyholder occupies between time k and k plus 1, given that the policyholder has an a priori mean risk that is equal to theta. So the Lk random variable should take a value between 0 and s, the possible levels in the scale. So its distribution consists of the probabilities listed in the vector here on top of the sheet. So we have to express what is the probability that this Lk random variable for an a priori mean equal to theta will be equal to 0, will be equal to 1, and so on, will be equal to s. If you specify all of that, all these probabilities, you specify then the whole distribution of your state random variable. Having the distribution Lk, the distribution of Lk plus n follows as the product of the distribution of Lk and the n-step transition matrix. And you can understand this in the following way. So the probability that Lk plus n equals 0, for example, is the probability that the policyholder occupies level 0 at time point t equal to k plus n. So he will be in level 0 at time k plus n if he was in one of the levels in the scale at time k, and then moved to level 0 in n steps. So the total probability of all the possible trajectories or paths, that's what you see expressed at the bottom of the sheet. So that is the probability that your policyholder is in level 0 at time t equal to k plus n.